All right, so we are going to start Unit 11. Unit 11 is going to be investigating the state of matter that we call gas. And today's lesson is going to focus on the four measurable quantities that we can collect data on in a lab setting when it comes to gases. So there's something called the ideal gas law, and we're going to spend time learning how to calculate the ideal gas law on Monday in our next lesson. But for now, we're going to really focus in a little bit on the four, like I said, the four individual measurable quantities of a gas. The first one is volume. And at some point or another, we said that volume of a gas is the amount of space that the gas itself can occupy. So when you think about it, if you take a balloon, right, and you blow that balloon up, the inside of the balloon is that balloon's volume. And if you take that balloon and you let all of the air out of that balloon, that air has to go somewhere. So it's going to fill up whatever container it's put in, which in this case happens to be maybe the room, right? So the volume of the gas is the volume of its container. And the gas will expand to fill whatever container it's put in. There is a standard unit of measure, which is the liter. So in this case, this is our standard unit of measure. And sometimes you're going to be asked to convert from liters to milliliters. And in order to convert from liters to milliliters, you need to remember the relationship that 1 liter of anything is equal to 1,000 milliliters of that anything. So volume is one of the measurable quantities of a gas. The next measurable quantity of a gas is something that we identify as the amount of gas. And the amount of gas is basically the number of particles in that gas, or the number of particles that make up that gas. The standard unit of measure there is simply the mole. And so we've worked with the mole over the past few units, or a couple units rather, and so we're going to revisit that a little bit in this unit as well. So if you remember that 1 mole of anything is equal to the mass on the periodic table. Commonly called the molar mass. So just like we did in our last unit, you had to calculate the molar mass of the substances you worked with in the lab. You went to the periodic table, you grabbed the masses on the periodic table, and you simply added them up. And that's basically, that will translate to the number of moles that a gas can have. The next unit of measure that we can collect is something that we call pressure. The pressure is really measured as the amount of collisions that the particles of a gas have with the container walls. So what that really means is that when particles are moving and they are colliding with container walls, that collision has some amount of force, and that force is equal to what we call pressure. So the standard unit for pressure in chemistry, when we talk about gases, is something called the atmosphere. In the United States, when we talk about pressure, like you fill up a car tire or you fill up a bicycle tire, it's usually in something called the PSI, which is pounds per square inch. But we don't use the PSI in chemistry. We use the atmosphere. But there's some other variables or other ways that we can measure pressure in chemistry. One of them is 760 with a decimal point millimeters of mercury, mmHg. Another one is 101.325 kPa, and that is, so millimeters of mercury, mmHg is millimeters of mercury. kPa is something called the kilo Pascal. I think I spelled that wrong. Kilopascal. And then the last one is something that we call the torr. So 1 atmosphere is also equal to 760 with a decimal point torr, which the torr is an abbreviation of the individual who kind of figured out how to make a barometer work, Torricelli, way back when. So these are our 3 different ways that we can convert between the standard unit, which is atmospheres, and some other ways that we measure pressure in chemistry. And then the last one is temperature. And temperature in chemistry is a little bit different than like when we think of temperature. A lot of times we think of temperature like, oh, it's hot outside, or oh, it's cold outside, or I've got a fever, I'm burning up. But really, temperature is a measure of how fast or how slow the particles of that particular substance is moving. So in chemistry, we're really talking about the kinetic energy, that is the energy of motion of the particles in the system. So the faster the particles are moving, the more the higher the temperature is going to be. However, we in chemistry, especially in gas law unit, we use something called the Kelvin temperature scale. And there's a common conversion because we don't have Kelvin thermometers in chemistry in our chemistry labs. We have Celsius thermometers, but the conversion from Celsius to Kelvin is actually really pretty easy. So we have degrees Celsius plus 273 will equal Kelvin. Okay. Now I want to go back real quick and identify the letter that we will use for the variable. For temperature, we're going to always use a capital T. For pressure, we're going to use capital P. For amount of gas, this is going to be kind of the weird one. We are going to use lowercase n. Okay. And then for volume, we're going to use capital V. Now, one of the reasons why we use lowercase n for the amount of gas is because we use m, like for moles or whatever. We use it so often and so many other things in chemistry that we just decided that n would be a great value for or a way to represent number of moles, and that's not going to be too big of a deal. Now, why don't we use the Celsius temperature scale? Why don't we use Fahrenheit? Well, Fahrenheit is really not an awesome system, in my opinion. But the issue is that if temperature is actually the measure of kinetic energy, that is how fast the particles are moving, it would make sense for us to not have a negative value, because if the particles are slowing down, the atoms or the molecules are slowing down, but they're still moving, they wouldn't have a negative value because they'd still be moving. So the Kelvin temperature scale, when it says that it's at 0, is a temperature where we can assume that all particle movement has stopped. So the particles have slowed down to the point where they're actually stopped moving. And in theory, those particles would also stop moving. The subatomic particles would also stop moving, like the protons and the neutrons and the electrons. So at that point, we've gotten to 0 because there's absolutely no particle movement. Absolute 0 has never actually been reached in the lab, although we've gotten really close. We've gotten to like 0.00001, something like that. But there's always some barrier that makes it really difficult for us to get to absolute 0. So now that's why we use Kelvin, because it doesn't have a negative value. All right, so now we just went through a bunch of stuff, and I'm going to try to make sure that we have all of our information that we just talked about in one spot. So when you're in your notes, you don't have to go flipping back and forth. You can just look for this particular table. Okay, volume, right, is going to be capital V, and it's going to be 1,000 milliliters is equal to 1 liter. Okay. Remember, these units here are going to be really important coming up shortly. Amount of gas is going to be the mass on the periodic table. in grams equal to 1 mole. And remember, that is going to be N. Pressure is going to be, there's going to be three different types of pressure that we can measure. So 1 atmosphere, ATM, is going to be equal to 760 with a decimal millimeters of mercury. 1 atmosphere, ATM, is going to be equal to 101.325 kilopascal or kPa. 1 atmosphere, ATM, is going to be equal to 760 torr. And then lastly, the conversion from degrees Celsius to Kelvin is degrees Celsius plus 273. Okay, so now you have a great all-in-one spot, I guess, place for you to look at when you're looking at your common conversions. And speaking of common conversions, one of the things that we're going to ask you to do is convert between units. So in this example, or in this example, we ask you to first identify the gas property that's being converted and then do the convert to the standard unit. Okay, so we're going to have to do a little bit of like going back and forth here a little bit. But first of all, the first one is 500 milliliters of H2. ml, milliliters, tells me that the unit is going to be a volume unit, ml. Think about like, when you get a bottle of water, it's like 500 milliliters or something like that. That's how you think about it as volume. So milliliters always tells you that you have volume. So now that one we're going to convert to the standard unit. So we're going to convert milliliters to the standard unit of liters. And if we're going to convert milliliters to the standard unit of liters, we have to remember that one liter is equal to 1,000 milliliters. So I'm going to take my 500 with a decimal point milliliters, put it over 1, and I'm going to set this up so my unit of milliliters cancels out. So 1,000 milliliters on the bottom, 1 liter on the top, and when I multiply straight across and divide, I get a value something like 0.500 liters. Noting here that milliliters cancels out, and so my final answer, like I said, is 0.500. And so 500 over here has a decimal point at the end of it, so it has 1, 2, 3, so it has 3 sig figs. So when I come and get to my answer needs to have 3 sig figs. So I'm going to draw that arrow and count 1, 2, 3. So that's going to be my 3 sig figs there. So again, my final answer is going to be 0.500 liters. Okay, next one. 25.4 grams. Okay, so when I see grams tells me that I'm working with amount of gas. So that means that in this case, I'm going to be converting from grams to moles. And when I go from grams to moles, I need to use the masses on the periodic table. So the first thing I'm going to do is I'm going to calculate my molar mass. So it looks like I have 1 carbon times 12.01. And I have 2 oxygens times 16.00, which will give me 32.00 grams of oxygen. I'm going to add those up, and I'm going to get something like 44.01 grams of CO2 equal to 1 mole of CO2. And so now I'm just going to use that molar mass and set this up so I can cancel out my units. So I'm going to take the, 25.4 grams of CO2, put it over 1. I'm going to put 1 mole of CO2 on the bottom and 44.01 grams of CO2 on the bottom. And then I'm going to grab my calculator. I'm going to take 25.4 times 1 divided by 44.01, And my calculator is going to give me something like 0.577141558.7. So we have to go ahead and assess significant figures real quick once. I'm going to draw an arrow here and count 1, 2, 3. So this is 3 sig figs. This has 1, 2, 3, 4 sig figs. So my final answer is going to have 3 sig figs. So I'm going to count 1, 2, 3, draw a line. That 1 does not round that 7 up. So my final answer is going to be 0.577 moles of CO2. Next one is 30 degrees Celsius to or 30 degrees Celsius. So this degree symbol, Celsius, tells me I'm thinking about temperature. Okay. So I'm just going to use that formula. So the formula, so I'm going to be converting from degrees Celsius to Kelvin, and that formula was degrees Celsius plus 273 equals Kelvin. So I'm going to take 30 degrees Celsius plus 273, which will give me Kelvin, and 30 plus 273 is 303. So my final answer here is going to be 303 Kelvin. And then lastly, I have this other example here where we're going to be looking at, because process of elimination will tell us, but millimeters of mercury means that we're dealing with pressure. Okay. And we're going to convert to the standard unit, and the standard unit says I'm going to go from millimeters of mercury to atmospheres. So now I need to remember my different conversions, right? And if I look right up above in my note sheet, I see that 760 millimeters of mercury equals 1 atmosphere. So I'm going to go back up here and look. Oh, see 760 millimeters of mercury equals 1 atmosphere, ATM. So I'm just going to write that down here. 760 millimeters of mercury equals 1 atmosphere, ATM. So I'm going to take 750 millimeters of mercury, put it over 1, and set this up so the units cancel out. So 760 with a decimal point millimeters of mercury, and 1 atmosphere on the top. So let's see here. 750 divided by 760 gives me, I don't know, something like 0.9868421,053, something like that. So let's assess significant figures. Okay, so now in this case, 750, the way it's given to me, does not have a decimal point. So I'm going to draw my arrow this way until I get to that first non-zero digit, count 1, 2. So this has 2 sig figs. 760 does have a decimal point, so I'm going to count 1, 2, 3, so 3 sig figs. So my answer needs to have 2 sig figs. So I'm going to draw this arrow coming in here and count 1, 2. I see that 6 does round that 8 up. So my final answer here is going to be 0.99 atmospheres. And so that's how we do pressure conversions and temperature conversions and amount of gas or mole conversions and volume conversions in the gas law unit. All right. Now, the next thing we need to talk about briefly is some vocabulary in terms of these variables and what does that mean and relationships and all that stuff. So when you look at a graph and the graph says that one variable increases, so like in this case, you might be like, I don't know, something like, let's say 1, 2, 3, 4, 5, 6. And this one might be something like, I don't know, 3, 6, 9, 12. So basically the variables on each axis are getting bigger. They're both increasing. So when one variable increases and the other variable also increases, we call that a direct relationship. So if we have an increase, oops, wrong one. If we have a variable increasing and the other variable on the graph also increasing, that's a direct relationship. And the same can be said if one variable decreases and the other variable also decreases, that's also a direct relationship. So these variables will appear on opposite sides of the chemical equation, or not the opposite sides of an equation. So that's what we call a direct relationship. Another example would be what would happen if one variable increases while the other one decreases. So this could be something like, let's see. So this could be something like 1, 2, 3, 4, 5. And this could be, again, something like 6, 5, 4, 3. Let me do it better. This should be like 1, 2, 3, 4, 5, 6. Okay. So looking at this graph, right, my initial data point is way up at 6 and 1, right? And then what ends up happening is that as the x-axis's values get bigger, the y-axis values get smaller. So this is an example of when one variable increases and the other variable decreases. Those two variables end up on the same side of the equation. So in this case, that's another major relationship that we have, and we can use those two ideas of an inverse relationship or a direct relationship to make some claims about what can happen with a gas. So we're going to practice that right here. So in this case, we have that the volume of the gas is decreasing, right? So the volume here is going to decrease. So what will happen to the pressure, right? So the pressure, so the question is, what will happen to the pressure? Okay. So if the volume goes down, and we're going to assume all the other variables are constant. So if the volume goes down, we can make a claim that the pressure will increase. Now, we have to remember that the definition of pressure is the number of collisions with the side of the container that the particles have. Now, the evidence for this would be that the volume of the container is going to decrease. Okay, so let me just draw a real quick picture here. So if I have a box and I take that same box and I squish it down to about half the size, and if I put inside that box, say something like 4 particles, right? Those 4 particles are going to fly around and hit the sides of the container. But if I take that same box with those same 4 particles and I make the box half the size, those particles are going to fly around and hit the container more. So the reasoning that we can give here is that the particles will have less space to move around, so the number of collisions will increase. All right, so that's one example. Let's take a look at another example. Now we're talking about the number of particles of a gas will increase. So we're saying that we are going to have the number of particles of a gas increase, and the question will be, what will happen to the pressure? What will happen to the pressure? Okay, so in this case, if we increase the number of particles, the claim that I would make, right, would be that the pressure will increase. And the evidence for that is that we have the number of particles increasing. So if I try to draw a picture to represent that, right? So I'm going to have box A, and then I'm going to have like the same box, right? And so if I put like 4 particles in the first box, and then I dump in those 4 particles, but then I add in something like, I don't know, let's say I add in like 4 more particles, right? Those particles will increase. Because those particles have increased, those particles have more opportunity to collide with the container walls than the first 4. So the way that we would identify that or talk about that is we would simply say that when there are more particles, so there will be more collisions. So there are more particles. So there will be more collisions with the container wall. All right, next one. If the temperature of the gas increases, what will happen to the pressure? All right, so now we're talking about temperature. So if the temperature of the gas increases, what will happen to the pressure? So we're still looking at pressure here. Okay. In this case, I would venture to guess that if we know that if one of the things that we know about one of the things that we know about pressure, or about temperature rather, is that if we increase the temperature, the particles are going to move around faster. So my claim here will be that pressure will increase. The evidence I have is that the temperature is going to increase. And so let me try to draw this picture here. So if I take a container and I put 4 particles in it, and let's say they're just moving, right? And I take that same container with those same 4 particles, and then I heat them up. So that's a candle, right? So I heat that container up. So if these particles are moving, right, I'm just going to give them little arrows to show that they're moving. Oops, I don't know what picture that was. There's an arrow. There's an arrow. These particles are going to be moving with a much faster rate. So I made the arrows bigger to illustrate that the particles are going to be moving faster. And so if they're moving faster, they're going to collide with the container wall more often and with more energy. So we're going to say that the particles will have more energy and moving faster, so their motion will increase. So the number of collisions will increase. Now, one more example, and then we'll call it a day. All right. This one says if the number of particles of a gas increase. So now we're talking about number of particles again, right? So the number of particles of a gas increases. What will happen to the volume? So now we're going to have what will happen to the volume. So if I add more stuff, we can assume, or at least we can probably venture to guess, that the volume will also increase. And my reasoning is that the number of particles will increase. So again, if I try to draw a box here and I say I've got 4, right? If I add a ton more, we want those 4 to like kind of spread out as much as possible. So if I add like 4 more, they're going to kind of they're going to increase space. So in this instance, we would simply say more particles will take up more space. So the added particles will take up more space. Now, the last thing I want to do is go back and talk a little bit about what type of relationship each of these things are. So I'm going to go, I'll start with this one. So the number of particles increased, right? So in this case, the number of particles increased, meaning that my volume would increase. So in this instance here, this is going to be a direct relationship. Moving back up here we have the temperature increased. And we're also stating that the pressure increased. So this is also going to be a direct relationship. Boy, I don't know what word that is. Looking at number 3, here we have the number of particles increasing. So I've got particles increasing. And we're saying that the pressure is going to increase because that was our explanation. So that tells me that this is going to be also a direct relationship. And then the last one says, here we have the volume increasing. Oops. So the volume, we said decreased, but then we said that the pressure increased. So because they're kind of opposite of each other, we're going to say that this is an inverse relationship. So we covered a couple of things. We covered the 4 main measurable quantities, so which was volume, number of moles, temperature, and pressure. And then we talked a little bit about how those variables relate to one another when you change one of them. So the homework that's going to be associated with this lesson is the first worksheet in the packet. It is a 2-sider, and we will go through the answers on Monday. Have a good weekend. Talk to you later.